Hello, welcome to Regular Achievers Educational. So today we're going to continue with our paper 2 review, and we're going to be moving on to another topics on paper 2. So far we've looked at forces, waves. Today we'll be looking at magnetism and electromagnetism. And also have it at the back of your mind that after reviewing this topic, we're going to also look at a practice paper, a practice question in line with the topic. This topic explores how magnets interact, how magnetic fields behave, and how electricity and magnetism combine to produce motion, induction, and useful devices. Magnets and poles. Magnets have the north and the south poles, and the law of magnets states that like poles repel and opposite poles attract. Permanent magnets always have fixed poles. Induced magnets become magnetic only when placed near a magnet, so their domains align temporarily. Common magnetic material include the likes of your iron, the nickel, and the cobalt. Magnetic fields. Magnetic field lines shows the direction and strength of the field. It helps you to know whether it's going the clockwise direction, where it's moving from, where it's going to. Lines always go from north to south, and the field is strongest closest to the poles and weaker further away. Okay, when you place it far away from the magnet, okay, it gets more weaker, but when it is closer, it gets more stronger. So plotting compasses will help you to be able to map the field around the magnet. Earth's magnetic field. Earth acts like a giant magnet due to its core. A compass aligned with Earth's field pointing towards the magnetic north, which is actually a magnetic south pole. This explains why compasses always point north. Current and magnetic field. A current in a wire creates a circular magnetic field around the wire. So the right hand grip rule shows the direction of the field. Increasing the current will strengthen the magnetic field. Increasing the distance from the wire will weaken the magnetic field. Solenoid. A solenoid is a coil of current carrying wire and produces a strong magnetic field similar to a bar magnet. Adding an iron core will increase the field strength, and field strength also increases with more turns, high current, length of coil, and the soft iron core. The motor effect. When a wire carrying current is placed in a magnetic field, it experiences a force. The direction of that force is at right angles to both the field and the current. This effect is the foundation of how electric motors work. Fleming's left-hand rule. This is used to find the direction of the force on a current-carrying conductor. Okay, and in doing that, we're made to understand that the thumb represents the force. The first finger shows the field, whether it is north or to south. The second finger represents the current, whether it's a conventional current, and all three directions, they are perpendicular to each other. Electric motors. A coil sits between two magnets. So current flows through the coil, and as a result of that, motor effect creates forces. So one side is pushed up, the other pushed down, and that will now cause a rotation. So the coil spins continuously because the direction of current switches each half turn. Electromagnetic induction. A voltage is induced when a conductor cuts through a magnetic field or the magnetic field around it changes. So if a part of a complete circuit, a current will flow. The induced current creates its own magnetic field that opposes the change that created it. Transformers. Transformers change the size of a voltage using two coils and the magnetic core. AC, in the primary coil, it creates a changing magnetic field, inducing alternating current in the secondary coil. So more turns on secondary, step up transformer, and when we have few turns on secondary, we have step down transformers. Microphones. Sound wave cause a coil to move within a magnetic field, and this movement induces a current that matches the sound signal. So this electrical signal can then be amplified or recorded. Loudspeakers. These work as the reverse of the microphones. So a current passes through the coil in a magnetic field and the coil removes, then this vibration moves a cone, producing sound waves in the air. In conclusion, magnetism and electromagnetism explain how magnetic fields interact with electrical current to create forces, motion, and electrical energy. From motors and generators to transformers, microphones, and speakers, these principles form the foundation of many modern technologies. So we'll now proceed further now to take a look at a relative past paper on magnetism and electromagnetism.
All right, so basically, we're going to continue from where we stopped in the material by taking a look at a typical sample of GCSE standard paper in line with the topic we're treating. All right, so let's take a look at two numbers of questions together. The first question there, it says that some metals are magnetic and others are non-magnetic. Which of the following metal is magnetic? Which of the following metal is magnetic? So basically, we need to understand that even though metals they are magnetic, there are some metals that are not magnetic. Okay, so they say which of the following metals is magnetic? Even though iron is a metal, it's not magnetic. Copper is a metal, it's not magnetic. Zinc is a metal, it's not magnetic. The right answer is cobalt. The next question says, Figure 1 shows the magnetic field lines around a bar magnet, and the cycle represents plotting compasses. The cycle represents the plotting compasses. So we are asked to draw one arrow each in the cycle to show the direction of the magnetic field at each place. So the direction of the magnetic field at each place is going to follow this direction. Okay, it's going to follow this direction. This is the direction it has to follow. Then the next one says, Figure 2 shows magnetic field lines around a bar magnet. Then the question says, which letter shows where the magnet is the strongest? You can see we have A, B, C. So it's at this point of entrance limit. That is when it is quite very strong. Then figure 3 shows the magnetic field lines between two bar magnets. So there's a which diagram shows how the magnet are arranged. It's going to be south-south pole because there is a repulsion in this case. There's a repulsion. There's no attraction here. Then the next one says, a teacher demonstrates how currents in a wire creates a magnetic field around the wire. Figure 4 shows the wire passing through a piece of cardboard. The current can be switched on and off. Describe how the teacher can use a plotting compass to demonstrate the magnetic effect of the current in the wire. So the first thing is while the current is being switched on and off, it's going to cause the compass needle to move. That's one of the things that is quite going to be observant. Another thing is that while the current is being switched on and off, the teacher can be moving the compass around the wire. So either of the two methods is actually applicable by the teacher. The next question says, the teacher decreases the current in the wire. The teacher decreases the current in the wire. How does the strength of the magnetic field around the wire change? When there is a decrease in the current in the wire, then there's going to be a decrease in the strength of the magnetic field around the wire. So the next question, the teacher reverses the direction of the current in the wire. What happens to the magnetic field around the wire? When there is a reverse in the direction of the current, then there is going to be a change in the direction as well. There's going to be the change in the direction of the magnetic field around the wire. There's going to be a change. There's going to be a change in direction as well as a result of the reverse in the direction of the current in the wire. The figure 1 shows the magnetic field pattern produced when there is a current in a wire. Then I say, what do the arrows on the magnetic field line represent? It's simple and straightforward. The arrow, as you can see, what they do represent is direction. They let you know the direction that is following. That is following a clockwise direction. So that is what the arrow represents. Then I say, how could the strength of the magnetic field increased? How could it be increased? Just like we've seen in the last question before now. How it could be increased is by increasing the current in the wire. When the current in the wire increases, the magnetic field strength also will increase. Then we have the next question that says the wire is coiled to make a solenoid, which diagram in figure 2 shows the magnetic field pattern that is produced when there is a current in this solenoid. When there is a current in the solenoid, it's followed this pattern for the magnetic field pattern. And the next one, figure 3, shows the parts of an electric bell. You can see some of the part of the electric bell right here. And then the figure 4 shows an incomplete sequence of how the bell works. So we are asked to use the option below. They say write one letter in each box to show the correct sequence. The correct sequence. So the first one there, they say you close the switch. So after closing the switch, then there is a current in this circuit. So you write D here. Then after that, we were made to understand that there is going to be a magnetic field being created around the magnet. There's going to be a magnetic field created around the magnet. Then the next thing is that a resultant force will act on the iron arm, causing it to move towards the electromagnet. And then we have the iron arm will now move away from the brass contacts and hits the gun. Boom. Then the last thing is that the iron arm returns to its original position. So, you know, if you use a bell door or a doorbell, that is the principle that it follows before you hear the sound. The next question says, which of the following would increase the resultant force on the iron arm? Which of the following will increase the resultant force on the iron arm? And that is simply when there's a decrease in the distance between the electromagnet and the iron arm. When there's a decrease between the electromagnet and the iron arm, then there's going to be an increase in the resultant force on the iron arm, the way it's going to sound. Then the next question says, the iron arm of the bell vibrates with a frequency of 6.25 Hertz. Calculate the period of the iron arm. They've already given you the equation to use. You just need to put the value 1 over 6.25. And if you do 1 over 6.25, that will give you 0.16 seconds. All right, we're doing great. The next question, it says the sound waves produced by the bell, they are longitudinal. The sound wave that is produced by the bell, they are longitudinal. Figure 5 shows the position of the head particles at one point in time as the sound wave travels through the head. Then I say, which of the letters represents an area of compression? It's going to be at the midpoint that we have the area of compression. Then I say, when two magnets are close together, they exert a force on each other. Complete the table below to show if the magnet will attract or repel. This is unlike pole, so that means they're going to attract. This is unlike pole, so that means they're going to attract. This is like pole, that means they're going to repel. This is like pole, that means they're going to repel. Figure 1 shows the magnetic field around a bar magnet. Then it says, which statements are true for the magnetic field that is shown in figure 1? Which statement is true for the magnetic field that is shown in figure 1? The magnetic field lines point from south to north? No. The magnetic field lines all meet at a single point? No. The magnetic field is a uniform away from the poles? No. The magnetic field is strongest at the poles? No. The magnetic field gets weaker further from the magnet? Yes. The more it's closer to it, the more it attracts it back. But when it's far away, it gets more weaker. Figure 2 includes an electromagnet. Then I say, which metal is used to make the core of the electromagnet? That is going to be iron. Very, very super effective. Then I say, we should complete the sentence. The switch is closed, and when that happens, there is a current in the dash. There's going to be a current in the coil when the switch is closed. Then I say, the number of turns on the coil is increased. The current remains the same. How does this affect the strength of the magnetic field around the electromagnet? Whenever the number of turns of the coil increase, even though the current remains the same, it's going to cause the magnetic field to be much more stronger. Then the next question that says, the metal core was removed. The metal core was removed and the current still remained the same. How does this affect the strength of the magnetic field around the electromagnet? It's going to cause the electromagnetic field to be weaker in this regard. It's going to cause the electromagnetic field to be weaker because the metal core is already removed. Even if the current remains the same, the metal core, which is iron, being removed, then it's going to actually make the magnetic field around the electromagnet to be weaker in that regard. So basically, this is just few numbers of question, standard question on the topic we've treated. Do well to also do further studies in line with that. Do well to like, subscribe to this channel. Thank you and see you some other time. Bye-bye.